Hello and welcome to this video lesson on free energy change, and it's all about the feasibility of reactions. It has spec reference 3.1.8.2. And what we want to understand by the end of this video lesson is the following. Firstly, we want to understand that free energy change is the balance between these two concepts that we've dealt with just now, entropy and enthalpy. And free energy change is a balance between those two. And the free energy change determines the feasibility of a reaction, which is whether a reaction can or cannot happen. Secondly, after understanding what free energy change is, we're going to get mathematical and calculate some free energy changes using this equation. And lastly, we're going to understand that some reactions, the feasibility depends on temperature, as is suggested in the formula. And so we're going to calculate the temperature at which our reaction becomes feasible. So there's going to be a boundary temperature, and above or below it is going to be either feasible or not feasible. So that's what we're going to do. So what is free energy change? Well, it's a concept that's used to predict whether a reaction is feasible. So that's a key word, let's write it down. So whether the reaction is feasible, and what that means is whether it can possibly happen or not. And it doesn't necessarily mean it's going to happen spontaneously. A spontaneous reaction happens under standard conditions without any help at all. And a feasible reaction could happen, but some reactions are going to have such high activation energies that they need some help to start the reaction off. But a feasible reaction, once it's started, will continue to completion. And it's given the sign delta G. And a reaction is feasible if delta G, if the free energy change, is less than or equal to 0. And we have a formula for free energy change. It's given here. So let's just label all these to make sure we know what they are and what the units are. So this is our free energy change. Our delta G, and our units are joules per mole. I've normally been working in kilojoules per mole, but in this case with free energy change we are working in joules per mole. Delta H we're quite familiar with, and this of course is enthalpy change. This is enthalpy change, and in contrast to our normal units, the units for enthalpy change here, we're going to use joules per mole as well. Temperature is in Kelvin, and our entropy change, our delta S is our entropy change, and our units for entropy change are joules per Kelvin per mole. So you can see from the equation that free energy change is a balance between enthalpy and entropy. And so if, for example, you're going to have a exothermic reaction, then our enthalpy change is going to be negative. And if we have an increase in entropy, then delta S is going to be positive. But because we're subtracting it, that's going to make delta G even more negative. And that's what indicates a feasible reaction. So feasible reactions are particularly prevalent when you've got exothermic reactions where the entropy increases. So now why don't we just use that equation there to calculate a free energy change. Here's an example of a calculation we might have to do. So we're calculating the free energy change for this reaction, magnesium carbonate, decomposing into magnesium oxide and carbon dioxide. It's all happening at 298 Kelvin. and we're given the enthalpy change delta H at standard conditions, which happens to be 298 Kelvin, and our entropy change as well. So we're given that. So let's just remind ourselves our delta G, which is what our question is asking us for, is going to be our enthalpy change minus temperature in Kelvin times our entropy change. So we're just going to feed in our values. Our enthalpy change is 117. But just let me highlight this. Our enthalpy change, as is quite common, is given in kilojoules. But we need to use the same units throughout this equation. So we're going to convert that into joules per mole by timesing it by 1,000. So there we are. And then we're going to subtract this term here. Let's give ourselves some square brackets because we're going to put our temperature in first, 298. And that is going to multiply our entropy change, which we're given in the question as 175. It's already in joules per Kelvin per mole. Yeah, so all that remains to do is to plug that into our calculators, and out pops a positive 64,900 joules per mole. So you can see that in this case, delta G is positive, so the reaction isn't feasible at this temperature. So if you had some magnesium carbonate, it's sitting on the table at 298 Kelvin, it's not going to suddenly thermally decompose it into magnesium oxide, giving off carbon dioxide. That's not going to happen. It might happen at a different temperature, but not at 298. So here we have a picture of some calcium carbonate, and it's being heated to thermally decompose it into calcium oxide and carbon dioxide. So that introduces the topic of temperature to our free energy change. Let's just write down our equation first. Our delta G equals our delta H minus T times delta S. And firstly I want to just repeat something I said on the previous slide. So if we've got an exothermic reaction, delta H is going to be negative, and we've got an increase in entropy. If we've got one of those reactions, then that's feasible at any temperature, because both terms of that equation are negative, and so delta G is going to be negative at any temperature. Okay, the opposite of that, so let's just change colour. If a reaction is endothermic, right, so delta H is going to be positive, and we're getting a decrease in entropy, then at whatever temperature our delta G is going to be positive. So that's unfeasible. So those reactions are unfeasible at any temperature. Okay, so they're the clear-cut cases. So the third option is when a reaction is endothermic. So if it's endothermic and there's going to be an increase in entropy, then the reaction is feasible above a certain temperature. It's above a certain temperature because as temperature increases, our term T times delta S increases more than delta H is positive, such that delta G will be negative overall, and the reaction will be feasible above that certain temperature. And the last option is that the reaction is exothermic, so delta H is going to be negative, and there's a decrease in entropy, then the reaction is feasible below a certain temperature. So as you can see, if the delta H term is negative and the delta S term is negative, if T times delta S is greater than the exothermic enthalpy change, then delta G is going to be positive and it will be unfeasible. So it's unfeasible that at that certain temperature. However, if the exothermicness of the reaction is greater than the T times delta S term, then it remains feasible below that temperature. So here's an example we can look at whereby the reaction, let's just call it reaction 1, is an endothermic reaction. Delta H is positive, but there's an increase in entropy. Perhaps there's more molecules produced by the reaction, for example. And so this is one of the ones that are going to be feasible above a certain temperature. And let's look at that temperature. Let's look at first at say 300 Kelvin. Let's see if it's feasible at 300 Kelvin. We're going to write down our delta G equals delta H, take T delta S, and quickly substitute in all our values. Our delta H is 10, but in joules it's 10 times 10 to the 3, and minus temperature in Kelvin, we've said, is 300 Kelvin, times our delta S is 10. Right, and when we work that out, comes out at 7,000 joules per mole, a positive number. So that's not feasible. Whereas if we look at it at a higher temperature, let's say 1500 Kelvin, at 1500 Kelvin, our delta G this time is delta H is still 10 times 10 to the 3, but this time we're multiplying our entropy change by 1500, and so our free energy change in this case at 1500 Kelvin is minus 5000 joules per mole. So you can see that at 300 Kelvin it's not feasible, but at 1500 Kelvin it would be feasible. So what temperature would this reaction be feasible? Well, it's just feasible. When it's just feasible, delta G is going to be 0. And if delta G is 0, then from our equation we can just set it to 0, in which case our enthalpy change is going to be equal to the term T times delta S. And this we can rearrange for T, so T equals delta H over delta S, and in this case our delta H is 10 times 10 to the 3, and our delta S is 10, and so the temperature comes out at, I think, 1000 Kelvin, and at 1000 Kelvin it's just feasible, and at any temperatures above 1000 Kelvin then delta G is going to be less than 0, and therefore the reaction would be feasible. So just to be clear, we're going to say feasible at temperatures above 1000. So here we've got a more real example that that might be an exam question. Here we've got tungsten can be extracted from its ore, tungsten oxide, by reduction using hydrogen. So you've got tungsten oxide there plus your hydrogen gives you tungsten and water. And we're given an enthalpy change, but we're asked to find the minimum temperature at which the reaction becomes feasible. So first of all, of course, we have to find the change in entropy over that reaction. We're given the entropies of the individual reactants and products, but not the change. So first things first, let's just notice that we've got kilojoules per mole here. So first of all, let's just convert it into joules per mole. Then, if we're going to use our formula delta G equals delta H minus T delta S, we need to find delta S because we haven't got that yet. So, if you remember, our delta S is the sum of the entropies of the products minus the sum of the entropies of the reactants. So, in this case, our products are tungsten and water. So tungsten is 33, and we've just got 1 mole of tungsten produced, so that we can leave that at 33. But we've got 3 moles of water produced, so we're going to have 3 times the entropy of water, which is 189 from the chart. So that's the entropies of our products, and we're going to subtract from that the entropies of our reactants. So tungsten oxide, let's have a bit of a square bracket there. Our tungsten oxide is 76, and we've got 3 moles of hydrogen. So we've got 3 times 65 there, and so when we do that little calculation, the change in entropy comes out at a positive 329 joules per Kelvin per mole. So first job done, and second job is to find the boundary temperature. It's that temperature at which the reaction just becomes feasible, and you'll remember from the previous slide when we use the delta G equation and set delta G at 0, we can rearrange what remains to give us our temperature. Our boundary temperature is delta H over delta S, and we've been given in the question our delta H, and we've just calculated our delta S. So our temperature turns out at 356 Kelvin. So although it's an endothermic reaction, and therefore less likely to happen, all else being equal, than an exothermic reaction, what we can see is that there's a slight increase in entropy when the reaction happens. And because of that increase in entropy, when you multiply that by a temperature, then that trumps the endothermic enthalpy change, such that at temperatures above 356 Kelvin, the reaction becomes just feasible. Now, free energy graphs are very interesting, and what they do is they plot delta G versus temperature in Kelvin, and from that you work out your delta H and your delta S. And let's have a look at why, or how you can use them. We're starting off, of course, with our free energy equation. Delta G equals delta H minus T delta S. And the mathematical ones of you will spot that you can put this in the form y equals mx plus c. So we're just going to rearrange this a little bit. So we're going to keep delta G as our y, but we're going to make delta minus delta S as our m, and then T has to be our x, and then plus delta H is our C. So let's just write that down. Y equals mx plus c. So if you were to plot a graph where the y-axis was delta G and the x-axis was temperature in Kelvin, then from the gradient you could find delta S, and from the y-intercept you could find delta H. So let's have a look at that in more detail. So here we've got a graph of delta G against temperature for a particular reaction, and we're going to use this plot to work out our delta S and our delta H. And so first of all, let's work out our delta H, and we're going to remember that delta H is our y-intercept. Here's our y-intercept here. So what we can say is that delta H equals 40 times 10 to the 3 joules per mole. So in order to work out our entropy change, our delta S, we're going to need to work out the gradient. So let's work out a gradient. So for our gradient, we're going to use this point again, and we're going to use this point here. So our gradient, which is minus delta S, is going to be this point, which is minus 30,000, minus this point here, which is 40,000, which is, okay, so there's our delta Y, divided by our delta X, which is going to be our 500 Kelvin, take our 0 Kelvin. So our minus delta S comes out at minus 140, and so delta S equals 140 joules per Kelvin per mole. So let's just recap, make sure we've covered everything. Do we now know that free energy change is the balance between entropy and enthalpy? I think so. We've done a few examples, and we know about the feasibility of a reaction as well. And we've calculated a few using our free energy equation. So if we can tick these two. And we've also looked at some reactions and how their feasibility depends on temperature, and how to calculate the temperature by our rearrangement of our free energy equation by setting delta G equals 0. So we've done that as well, and we've just now had a look at a free energy change versus temperature graph in order to determine enthalpy changes, delta H, and entropy changes, delta S. So we've done this one too. Hope that's been clear. If not, watch it again. And if it's still not clear, ask me in class. Thank you very much.